Lab 3 by Anna Catherine Brewer. Part 1. Mass of the Black Hole. Introduction. A star is orbiting a black hole of unknown mass that is located at the origin. The star's mass is 2 × 10 to the 30 kilograms. We will assume that the black hole is the only force acting on the star. The experiment will be over the course of 1 day. Firstly, I will enter the starter code into GlowScript. I will then find the net force of the star for all points in my dataset. Lastly, I will determine the mass of the black hole. The main physics ideas I will be using in this experiment are Newton's second law, momentum, and the universal law of gravitation. GlowScript initial conditions. First, I entered the initial conditions into my code. This included G, the time interval of 1 day, and the mass of the star. Fixing the starter code part 1. I first calculated P initial and P final by using P equals mv. I then calculated delta V and P by using the formula final minus initial. I then calculated dP dt by dividing delta P by time. Lastly, I determined that Fnet is equal to dP dt. Fixing the starter code part 2. First, I calculated Fnet parallel from Newton's second law. I then calculated Fnet perpendicular by subtracting Fnet parallel from Fnet. Fixing the starter code part 3. First, I calculated the mass of the black hole using the universal law of gravitation and solving for big M. I then determined the length of the arrows of Fnet, Fnet parallel, and Fnet perpendicular. Results and observations. The orange arrow is Fnet, the blue arrow is Fnet perpendicular, and the red arrow is Fnet parallel. The star speeds up as it approaches the black hole. Fnet increases as the star approaches the black hole. The mass of the black hole is approximately 6.82 × 10 to the 33 kilograms. What does it mean? Question. How are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? Answer. The net force and the change in momentum are equal according to the momentum principle. However, the components of the rate of change of momentum are calculated from information that is given in the data, while the components of Fnet are just loosely predicted based off what was calculated for the rate of change of momentum. Analyzing results and conclusion. The deviations in the value of the mass calculated were probably due to Fnet being average and not exact for each time interval. Because all values were randomized and given, there are no adjustments that could be made. However, if I were to recreate this experiment to get more accurate values, I would use a smaller time interval to get more accurate data at each location. Part 2. Don't crash. Introduction. For the second part of this lab, the goal is to simulate a planet and a ship launched from its far side orbiting around the previously found black hole. We cannot crash into the planet or be sucked into the black hole. We will be using the mass of the black hole that we just found. The default time will be 1 hour. GlowScript Part 1. Firstly, I calculated the total net force on the planet and the ship by using the universal law of gravitation. GlowScript Part 2. Next, I used the velocity and position update formulas to simulate the motion of the planet and the ship. Lastly, I used trial and error to determine the launch velocity of the ship, which resulted in the ship approaching the black hole and not crashing into the planet. Results and observations. The launch velocity I decided on was -1 × 10 to the 8, -4 × 10 to the 6, 0 meters per second. The spaceship was pulled by the gravitational force of the planet and the black hole. The ship approached the black hole and immediately left the system. What if? Question. What initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? Answer. Through the process of trial and error, I found that if the ship is launched with an initial velocity of 2 × 10 to the 2, 7.1 × 10 to the 6, 0 meters per second, it will enter into an orbit around the black hole. Conclusion. With varying launch velocities, the ship can take 2 completely different trajectories. Because the data was simulated, there aren't many ways to redo this experiment with more accuracy. However, I think it would be fun to launch the ship from the near side of the planet and see how that affects initial launch velocity. And this wraps things up. Thank you for listening to my lab report.